All right, so we're going to look at differential equations in this particular lesson, and any equation that involves a derivative is called a differential equation. And I have to tell you that there are entire college classes built around the idea of a differential equation, and I think you're going to find that seems like it's a pretty good concept to build a college class around after you see it. And the order of the differential equation is the order of the highest derivative that is involved in that equation. Now, in Calc 1, we're going to just kind of confine ourselves mostly to what are called first-order differential equations. And they take just one antiderivative to solve, and fortunately, they're pretty straightforward to do. And the good news is that you've had a little bit of expertise in doing these already. So we're going to start out with a simple example here, and we're going to find all functions y that satisfy dy over dx is equal to secant squared x plus 2x plus 5. Okay, now the way to tackle this, first of all, is we're going to separate our variables. We're going to get all of the things involving y on one side and all of the things involving x on the other. So that means I'm going to have to multiply both sides by dx. So I'm going to get secant squared of x plus 2x plus 5, and this is all being multiplied by dx. Okay, now at this point, in order to solve this equation for y, because that's what we need to do, I need to get rid of that differential, and that differential right there too. The way that we're going to eliminate the differential is we take the antiderivative of both sides. And the antiderivative of 1 with respect to y is just going to be y. And then now we can start going term by term on this other side, and it's easy to do. So antiderivative of secant squared is tan x. Antiderivative of 2x should be x squared. Antiderivative of 5 should be 5x. And don't forget your c that we need to tack on to the end here. And that is your family of functions y that satisfy that differential equation. All right, now a quick word about the plus c. Why didn't you have two c's? Why didn't you put one over here and one over here? Well, first of all, when you subtract one unknown constant from the other, you still get yet another unknown constant, even if that constant is 0. So we might as well just mash them together into one and call it good. All right, let's look at a few more. Okay, so we're going to find all the functions y that satisfy dy over dx is equal to 3x squared cosine x plus cosine x. I want you to pause the video here and take a moment and try that one for yourself. All right, and you can see that without too much trouble, that's what it comes out to be, x third plus sine x plus c. Nothing really too involved here, pretty straightforward. And this is the solution of a family of functions, and this is what we call the general solution to the differential equation, a general solution. And that's because we have a plus c here, because we don't know which specific antiderivative we're dealing with. Now, note that we can't find the unique solution to a differential equation unless we have more info. And if the general solution is continuous, then the only thing that we need to know is the value of the function at a single point, and that is called an initial condition. So if I give you an initial condition along with a differential equation, then what we need to do is we'll be able to find what that mysterious c is. And a differential equation with an initial condition is called an initial value problem. And I think you're probably going to see where we solve this pretty easily here. And it's got a unique solution, and that unique solution is called the particular solution to the differential equation. Let's look at how that would work. Okay, so we're going to find the particular solution to the equation dy over dx is equal to e to the x minus 6x squared when the graph passes through the point 1, 0. Okay, so first step is we're going to find out what y is. And to do that, we need to multiply both sides by dx, and that's a critical step, and I'm gonna say this right now. We want to get into this habit today, right away. The reason why is because if you take the AP Calculus test and you go to do a differential equation and you don't separate your variables, it could be very costly to you on an FRQ. I've seen some initial value problems that are worth as many as 4 or 5 points on an FRQ question out of the 9 that are available. And if you fail to separate the variables or demonstrate that you're doing that, then it's entirely possible you may get no credit for that entire question, and then that really sinks you for that particular question. So keep that in mind as you work on these problems. Okay? So we're going to take the antiderivative of both sides, and we come up with e to the x here, and then this is going to be minus 2x to the third plus some mysterious c. Okay, so now that we have that information, I'm going to take this particular initial condition here when the x is 1 and the y is 0, and I'm going to plug that into my antiderivative for x here and y here. So let's see what that looks like. Let me get the color coding right here. Okay, so it looks like we've got e minus 2 plus c. So if I move everything over to the other side, I'm going to get c is equal to 2 minus e. That's going to be my constant right there. Or negative e plus 2, whichever you prefer, either is going to work out here. So now to find what the specific or particular solution is, I'm going to take this value of c, go back up to the point where I started solving for c, and put it in there. So I've got y is equal to e to the x minus 2x cubed, and then this is going to be plus 2 minus e for the particular solution. All right, pretty straightforward. Okay, let's try this one right here. You try this one on your own and see what you come up with. Careful, it looks like we might need to do a u substitution on that part. So I'm going to pause the video here and let you have a go at it. Okay, here's a good place to pick up, and you see what I did. I kind of separated this into 2 different problems right here, and then I went to work on the indefinite integral of e to the 2x. That called for a u substitution, and that's going to give me 1/2 e to the 2x plus c when I'm done. Now I'm going to bring that over here, but you need to remember that this c and this one are going to get folded together when we do our antiderivative, just to cut down on the confusion of too many c's. All right, absolute value, or antiderivative rather, antiderivative of 3x will wind up being 3/2 x squared. And now you can take all of this information right here and sub it in. So I'm going to put in 1/2, and then that's equal to 1/2 e to the 1 minus 3/2 times 1 squared plus c. Okay, well, after I go ahead and deal with the constants, I'm going to power this out. That's going to be 1, so I've got minus 3/2 here. I'm going to add that to that other side. So 1/2 plus 3/2 should give 2. Let's learn to write here. Okay. And then I'm going to have 1/2 e plus c. All right, I'm not a fan of these fractions, so I'm going to just double everything. And it doesn't matter what you get for c. 2 times a constant is a constant. So this is going to mean c is equal to 4 minus e. And that's going to mean that my final answer here is going to be, whoopsies, let's make sure we get it right here. It's going to be 1/2 e to the 2x minus 3/2 x squared plus 4 minus e. And that is going to be your original problem right there, the initial value. All right, if we got a discontinuity, it's not really too huge of a deal, fortunately. Let's go ahead and see if we can handle this one here at the point 0,3. So we've got dy over dx. Now, let's go ahead and just take the step of multiplying here, shall we? So 2x minus secant squared x, and this is all multiplied by dx. And then once again, I want to go ahead and I want to zip through the antiderivative here. So y is equal to x squared minus tan x plus c. And then lastly, what I want to do is put in my initial condition here, and you're going to see it works out rather nicely here. 3. Okay, so 3 here is equal to 0 squared minus tangent of 0, and then plus c. All of this is going to go to 0 right here. And so our c is equal to 3. And then our final equation is going to be x squared minus tan x plus 3. And there's your solution to that problem. Okay, well, now in this situation, we can't really find an antiderivative, so what we're stuck with is using the fundamental theorem of calculus, and with a little nod to part 1, as well as a little nod to our integral properties here. So find the solution to this differential equation for which f of 7 is equal to 3. Okay, well, if we try to do this, what we're going to end up getting is something like that when we separate the variables. And I'm not going to be able to get around that with the u substitution or anything else. So what I'm going to have to do when I take an antiderivative is I'm very much going to have to leave it like that and engineer a variable switch here. So this is going to be the definite integral from something to x of e to the negative t squared dt plus our mysterious constant. Okay, now you notice that I left the lower limit of integration open right now. There's a reason behind that. Your lower limit of integration is going to be whatever your x value is in your initial value problem. All right, now why is that the case? Well, here's why. When we go ahead and sub in to try to find what our c is, we're going to discover that these limits of integration are the same, and that entire thing goes to 0. And if that goes to 0, then c is equal to 3. That's just going to be what our situation looks like. Okay? So our final answer here is going to be y is equal to the definite integral from 7 to x of e to the negative x squared, or t squared rather, dt plus c. And that's what that looks like. All right, so what I want you to do now is here in a second, I want you to go ahead and pause the video and try to see if you can come up with a very similar solution. And if that's the solution that you came up with, then you've got this down pretty well at this point. Okay? So that kind of takes our look into some basic differential equations and brings us to a close here. In our next session, we're going to look at some things regarding separable differential equations, which might involve another step or two to solve, but they're still not so bad. We will see you in class.